Welcome students. This is for PharmD students lecture 2 for lipids. We had definitions and its classification, questions, details which we had seen in the lecture 1. Now in this lecture 2, analysis, analytical parameters for oils and fats, and definition for wax also we are going to see in this lecture. And here additionally we will see the difference between fats and oils and volatile oil, that means fixed oil, volatile oils and waxes. What are their differences in chemically and their examples? We can have a slide about that. And here the properties of oils and fats vary along with the degree of unsaturation, average molecular weight, and also acidity from hydrolysis. We know that esters of fatty acids are fats and oils. So when it undergo hydrolysis, the acid released can also decide the major property of fats and oil. A number of parameters are used for hair analysis which are included under physical constants and chemical constants. Physical constants are commonly identified and they are very important. I am not giving in detail in this lecture, giving only the instruments, applications and how it performs. The students have to refer and have a note on it. You have to prepare your own notes, that is very important. Listening lecture, noting down the hints and make notes by yourself. That will be more helpful for you in writing the final exam. Physical constants include like viscosity, specific gravity, refractive index, solidification point, etc. There are many actually. Flame point, slippery point, like that there are many physical constants. Additionally, for lipids are available, fats it is available. So it's important for the students to know about that. General ideas and knowledge is important for you to go for any public exams. Under the group of chemical constants, there the questions they are asking: estimation, analytical constants, analytical test, analytical estimations. These all questions we have seen in university question repeatedly asked for lipids. So conventionally, the parameters like iodine value, acid value, peroxide value, saponification value, unsaponification matter, Polanski value, there are many other things, or also we are having some discussion about that, which can give you some parameters, some identification. Purity can be identified for various fats and oil which is in the market and as well as which we produce, can be analyzed, can be quality control can be given by means of this chemical analysis and chemical constant estimations. In recent times, gas chromatographic determination, chromatographic estimation, chromatographic determination of fatty acid profiles have been introduced for identification of fats and oil. That's also many new technology have been identified and invented to do it. To reduce the time schedule for analysis can be done by new innovative instrumental analysis. Physical constants include viscosity, which we know that we can do it by means of Ostwald's viscometer. So the procedures and things should be made into a short form prepared by the student. Specific gravity, we might have heard about specific gravity bottle. There are 25 ml, 50 ml bottle capacity where weight per ml can be calculated comparing with water. But we have piconometer with thermometer to have the temperature control. As it is an oil, fats can be used. This is also another version of specific gravity bottle. Piconometer can be used. Refractive index, which we have heard about this Abbey refractometer, now digital refractometer as shown in the picture, which can give you the sin I by sin R, the refraction of the rays passing through a medium to another medium, is possible to read. Refractive index can be determined for the fats and oils. Solidification point, also an important point which can be done by freezing point tester. A digital value can be given by means of freezing point or solidification point. Even we can use the Telles apparatus, melting point apparatus, by means of using a low temperature can also be identified. The solidification point or the melting point of the fats can be determined. The variation is also possible. Now we are coming to the important point of the chemical constant value of oils and fats, in which we have many determination, especially we have seen about 11 determination. Number 1, iodine value. Number 2, saponification value. Number 3, hydroxide value. Number 4, acetyl value. Number 5, unsaponifiable matter determination. Number 6, acid value. Number 7, peroxide value. Number 8, crest test, or it is rancidity index, can be identified for oils and fats also. 9, ester value. Number 10, Richards missile value, or missile value you can say, instead of say missile, Richard missile value. Polanski value. There are still many, but still this 11 students should know about the detailed procedures and a short form of definitions and small calculation theoretically. Practically we are doing most of the analysis in the lab. You might have performed, so it will be easy for the students to remember the parameters and adjustment difficulties which come across in the real practical experiment. First one is iodine value, in which we need, here we have shown the conical flask, round bottom flask with an burette, but usually we can go for Elman-Meyer flask with an stropper. which can be given more efficient results. Iodine flask they can be called. It is defined as the weight of iodine absorbed by 100 parts by weight of the sample of fat or oil, which is used usually by means of starch as an indicator. Iodine value is a measure of the extent of unsaturation. How much the unsaturation is present in the fatty acid linked in the ester formation of fats or an oil. Susceptibility to rancidity increases for the oil or fat having higher iodine values. If there is more unsaturation, then we can suspect that the particular oil or the fat is having rancidity, deteriorated, spoiled, can be identified. First method for iodine value is Hubel's method. Addition of iodine. Iodine monochloride react with the unsaturated bond with the sample in the fatty acid. Adding a halogen at the carbon-carbon double bond site in the sample. Here you can see that sample RCH with double bond CHR dash. When you are adding with iodine chloride or iodine monochloride excess, it gives RCHI, the attachment. The bond is removed and it can be added with an halide of iodine in CHI single bond, CHI single bond and R dash. We can see in the reaction plus iodine chloride, the remaining iodine chloride. So this shows how many double bonds are there. Their utilization of the iodine will take place. So determination of reacted iodine now, the second step in this procedure. After the reaction, potassium iodide is added to the reaction product, causing the remaining iodine monochloride to form molecular iodine, I2. So you can see that remaining ICl, iodine monochloride plus potassium iodide forms potassium chloride plus potassium iodide and iodine, molecular iodine. Titration can be done. The liberated iodine is titrated with a standard solution of sodium thiosulfate. Now, using the starch as an indicator, the starch is used to indicate the end point of the reaction. As the liberated iodine reacts with the starch to produce a purple color, sometimes the color may be slightly different. Iodine plus starch plus sodium thiosulfate gives sodium iodide, and starch colorless can be identified as an endpoint in sodium thiosulfate. Wedge's method, the second iodine method, there is two methods are there. This is also same, a slight reagent preparation difference. The reaction with unsaturated bond present in the sample, iodine monochloride ICl in glacial acetic acid reacts with the unsaturated bond in the sample, resulting in halogenation. So same reaction which we shown in the last slide. The iodine chloride react in the presence of glacial acetic acid, gives the iodine attachment with the carbon atom present in the double bond, and remaining ICl, conversion of the iodine monochloride or conversion of molecular iodine from iodine monochloride. The excess iodine monochloride ICl is treated with potassium iodide as shown in the last reaction, and water is converted into, that means potassium iodide and water is converted into molecular iodine. ICl plus potassium iodide KCl and Ki with a molecular iodine. Titration. The amount of iodine formed is determined by titration with the sodium thiosulfate and starch as an indicator. So as the reaction which we seen in the last reaction, like iodine with starch as an indicator, when you are titrating with sodium thiosulfate, you will get sodium iodide and starch colorless with the sodium thiosulfate. So this indicates what's the amount of iodine is utilized for how much double bonds are present in the sample can be identified by the iodine value. Significance of iodine value. The degree of unsaturation can be known with the help of iodine value. Drying character of oil can be determined. Adulterants can be recognized. Quantity of fats or oil required for converting them into soap can be determined. Calculation. Calculate the iodine value from the expression of 1.269 weight by volume, where V is the difference in ml between the titration. That means blank versus the assay. Blank means without sample we have to perform the assay, perform the titration. And weight of the sample which is taken, even though it is a liquid, you should write in grams of sample should be taken. So you can see here some of the value which is given. Iodine values, like for butter it is 26 to 28, lard it was 46 to 70, and tallow fats you can see 30 to 48. Edible oils like cottonseed oil, it showed 105 to 114. Soybean oil 128 to 143. Sunflower oil 140 to 156. Non-edible oil like tongue oil 160 to 175. Linseed oil 170 to 185. This is a picture which can be shown. Fresh oil, as you can see, that is yellowish, bright, attractive color. Rancid oil, slightly you can see deteriorated, which has more iodine value because of presence of more unsaturation may take place due to mold development or bacterial attack in the product. Next step, when you want to talk about the saponification value. Saponification value, it is defined as the number of milligrams of potassium hydroxide. We should know about the potassium hydroxide. Molecular weight of potassium hydroxide also have an important play in this calculation. That in the lab, even I have explained about the molecular weight and how they are giving the number for your calculation is determined from the moles per unit required to neutralize the fatty acid. Milligrams of potassium hydroxide required to neutralize the fatty acid. That is the definition. Resulting from complete hydrolysis of 1 gram of sample of oil or fat. Saponification value occurs in an inverse proportion to the average molecular weight of fatty acid present in oil. This value is normally applied for butterfat, coconut oil, in which lower fatty acid glycerides occurs in high content. You can see the calculation. Saponification value is equal to A minus B means assay minus blank. Assay with sample, blank without sample, you will be having a tighter value into 28.05 divided by weight in grams of the sample. I was explaining about 28.05 was the moles per unit calculated from potassium hydroxide. You can see that molecular weight and this number have been derived from the moles per unit or a concentration which is preferred for the experiment. Number 3, hydroxyl value. It is defined as the number of milligrams of potassium hydroxide required to neutralize the acetic acid capable of combining by acetylation. How much hydroxy group? Then only that much acetylation takes place with 1 gram sample of fats or oil. So definition, a number of milligram of potassium hydroxide required to neutralize the acetic acid capable of combining by acetylation with 1 gram of sample of fats or oil. Number 4, acetyl value. It is the number of milligram of potassium hydroxide required to neutralize the acetic acid obtained when 1 gram of acetylated oil is saponified. Acetylated oil is saponified. Except castor oil, acetyl value will be 150. Most of the oils and fats have low acetyl value, 3 to 15. Unsaponifiable matter. It is matter present in fats and oil which after saponification by caustic alkali and subsequent extraction with an organic solvent remains unvolatile on drying at 80 degrees centigrade. Remains unvolatile on drying at 80 degrees centigrade. It indicates or includes sterols, phytosterols and cholesterol, that is unsaponified or unsaponicable matter, oil-soluble vitamins, hydrocarbons and higher alcohols. Paraffin hydrocarbons can be detected by this method as an adulterant. If they are adulterated, paraffin's hydrocarbon can be easily detected from this unsaponificable matter presence in any oils and fats can be determined. Acid value is an important parameter, important chemical identification analysis for fats and oil. It is defined as the number of milligram of potassium hydroxide required to neutralize the free acid present in 1 gram sample of fats or oil. Generally, rancidity causes free fatty acid liberation. Hence, acid value is used as an indication of rancid state. Acid value is equal to, volume should be in ml of 0.1 mole by potassium hydroxide consumed, titer value into 5.611. 5.611 is also comes from the molecular weight of potassium hydroxide. As we are using 0.1 molar, 56.11 is the molecular weight of potassium hydroxide. It's divided by 10 and divided by the whole divided by weight of the grams in the sample. So the titer value and the blank should be identified for acid value, which you are performing in the laboratory. So I'm just going to the next step. So it is possible for the student to get the detail. Peroxide value, define or definition. It refers to the number of milliequivalents of peroxide, oxygen, hydroperoxide, that means, present in 1 kilogram of sample, oil or fat. Procedure: Dissolve weighed amount of 1 kilogram of fats or oil in glacial acetic acid. Add excess potassium iodide solution and titrate the resultant solution with standard sodium thiosulfate using starch solution as indicator how you performed in iodine value. See the reaction. Acid react with the potassium iodide in heating. It gives potassium hydroxide plus the ROH, whatever the radical which is present in the sample, and free iodine. Iodine then can be titrated with sodium thiosulfate to give sodium iodide and thiosulfate reaction, which gives you the indicator with the starch. Peroxide value is S minus B into N by W into 1000. S means the volume of the titrant by the sample, B is the titrant for the blank without sample, and N is the normality of sodium thiosulfate, and W is the weight of the sample taken in grams. Significance of peroxide value is used to determine the quality of the oils or fats by measuring the extent of oxidation in them. 0 peroxide value indicates that the fats or oils is of high quality. Low peroxide value represents the beginning of oxidation. Oils or fats having peroxide value more than 20 are said to be very poor quality. You can see here the table. 1 to 5 is low extent of oxidation. If the peroxide value is 5 to 10, then it is medium. If it is more than 10, then it is high. It's going to get rancid or getting oxidized. So peroxide value can determine the quality of the fats and oil. Chris test, rancidity index, it can be called. Due to rancidity, epihydrin aldehyde, epihydrin, it's a bitter taste, or manalone aldehyde are increased, which are detected by Chris test using fluoroglucinol, which produces red color with the oxidized fat. Ester value, it is defined as a number of milligram of potassium hydroxide, again comes, required to combine the fatty acid which are present in glycerides. So it can be very simple from a 1 gram of sample, the same definition of oil or fat. So this calculation can be done. Two things have to be determined: saponification value and acid value. Then the difference will give you the ester value. The difference between the saponification value and the acid value, not ester value, the saponification value and acid value. The difference between saponification value and acid value is the ester value. It gives the value of ester. Number 10, Richet-Missile value or Richet-Missile value. This value is measure of volatile water-soluble acid content of the fat. It is defined as number of milligram of N by 10. 0.1 normal or molar potassium hydroxide solution required to neutralize the volatile water-soluble fatty acid obtained by 5 grams of fat. Polanski value, it is determined the number of milliliters of N by 10 potassium hydroxide, 0.1 normal potassium hydroxide solution required to neutralize water insoluble. That is water soluble, this is water insoluble, steam distilled acid liberated by hydrolysis of 5 grams of fat. These 11 points and 11 chemical analysis is needed for you to specify very clearly in the answer book. Now we are having added in this lecture some details about Just a definition and example for waxes. Waxes along with fixed oils, the wax along also belong to the group of natural occurring compounds called lipids. They differ from fats and oils as they are long chain fatty acids combined with long chain monohydric alcohol or sterols instead of glycerol. That is the difference. Thus, wax only a single ester group, whereas fats and oils contain 3 ester groups. Usually, waxes are composed of unbranched carbon chain acids and alcohol. Properties of waxes: they are viscous solid substances which are greasy to touch and have characteristic shine. Waxes contain less content of unsaturated fatty acid, hence are difficult to saponify. Unlike fats and oil, they possess low saponification and iodine values. Waxes are immiscible in water but miscible in non-aqueous solvents. Waxes are easily hydrolyzed, hence they are used as protective coatings. They get hydrolyzed only with hot alkali or hot alcoholic alkali to yield soaps in the following manner. You can see the reaction. Hot alkali, when you are adding in beeswax, myrcene palmitate, you can see the structure of myrcene palmitate, how the long chain ester linkage COO, or you can see CH229 CH3, adding with hot alkali, it can be converted into sodium palmitate soap and myrcene alcohol insoluble, which can be also obtained in the waxes, but it is needed some heating hot. They are highly resistant to rancidification, getting oxidized or getting spoiled upon exposure to atmosphere oxygen. And number 6, waxes are hard, that we know in nature, and their melting points are very high, 35 to 100 degrees centigrade when compared to fats. Types of waxes depending upon their sources. Waxes are classified as follows. Plant waxes, the surface of leaves and stems, you can see in the plant fruits, some coating show a presence of wax actually. The waxy coating present in the surface of desert plants especially more protects them from excess loss of moisture due to evaporation in the hot condition in desert area. It allows protection to the plant for being infected by harmful or attacked by harmful organism. Example of carnauba wax obtained from leaves of carnauba palm of Brazil. Its main constituents is myrcene cerolate, the formula C25H51COO C31H63, which when hydrolyzed it yields myrcene alcohol, it yields myrcene alcohol C31H65OH and cerotic acid C25H51COOH. Melting point of carnauba wax is 80 to 87 degrees centigrade. It is used to make floor polishes and used in automobiles due to its hard and impermeable nature. It is also coated on carbon paper and mimeograph stencils, stencil paper. You know about the copy taking stencil paper. Now we have many printers are available, but stencil paper, when we want to more copies, there also which is used carnauba wax. Animal waxes, the most important function of these waxes is that they are widely used as protective agents. They are obtained from the surface of feathers, skin and hairs of animals. Most of these waxes are derived from marine sources. Example from sperm whales, bottlenose whales or bottlenose whales, bottlenose sperm whales and bottlenose whales. Number one, beeswax as an example, everybody knows. It is also derived from, we will study in detail about beeswax because they have asked many questions. This is just simply telling an example. It is derived from honeycomb of bees. It contains esters such as ceryl myristate C13H21COO C26H53. The myricyl and myricyl palmitate C15H31COO C3OH61. Sorry, there is a mistake. It is when you want to write about that carbon atom, it should be corrected about the myricyl palmitate. The melting point of beeswax ranges from 62 to 65 degrees centigrade. Materials such as shoe polish, candles and paper coating are prepared from beeswax. Spermacety. It is obtained from the heads of the sperm whale. It is rich acetyl palmitate of C15H31COO C16H33. Its melting point ranges from 42 to 50 degrees centigrade. It is used as a base in the preparation of ointments and cosmetic preparations. In pharmaceutical industries also, ointment base spermacety is used. Lanolin, wool fat, animal wax. Lanolin is obtained from wool or of sheep. It's a long process how to prepare. Consists of a complex mixture of high molecular weight alcohol, cholesterol and fatty acids such as carnaubic, oleic, myristic, palmitic, lanolinic and lenopalmitic acids. It is water soluble and used in the preparation of ointments. So now we have to, in this slide, it is needed for the students to revise and as well as to keep in their mind and prepare as hints. What is the difference between fixed oils and fats with volatile oil and with waxes? So 3, fixed oils, fats, volatile oils and waxes. What is its difference? Fixed oils and fats, volatile oil and waxes. When we come across fixed oils and fats, they are esters of fatty acids and glycerol. Volatile oil, they are complex mixtures of hydrocarbon and oxygenated compound. They do not contain glyceryl esters. Very important point, valuable point which the student should know in chemically. Waxes, esters of long chain fatty acids. They are esters, long chain fatty acids and long chain alcohols. So they both, fixed oils and fats and waxes, are more related, but they are harder and long chain. These things you have to remember. What is the property? Thick, greasy, liquid, non-volatile in nature. That is, fixed oils and fats are thick, greasy, liquid, non-volatile in nature. Volatile oils with characteristic odor, non-viscous in nature. You see the waxes, viscous, non-volatile solid substances. They are viscous, solid, non-volatile substance. Fixed oils are having food value. They have food value. But volatile oil, they do not have any food value. Waxes, they are not suitable for consumption usually. Fixed oils and fats, they are and they can be saponified, or they can prepare soap saponification, usually using aqueous or alcoholic alkali. Volatile oil cannot be saponified. Waxes are not easily saponifiable, but they are saponified only by hot alkali or hot alcoholic alkali, which we have seen just before. They can be saponified with hot alkali. Fixed oils and fats, upon exposure to air, they develop disagreeable odor and taste. Rancidity may takes place. But you see, upon exposure to air, they develop a change in color, odor, and becomes viscous, that's all. But waxes are resistant to atmospheric oxygen. And when you see fixed oil and fat, example, arachis oil, chalmogra oil, castor oil, we will see all this in detail. And volatile oil, example, eucalyptus oil, lemongrass oil. And waxes, you can see example, plant wax, carnauba wax, bayberry wax, animal wax, you can see beeswax, spermaceti, which is prepared from the sperm whale, nose whale. So these are some of the examples which we have discussed, and the difference also needed for the student. They may ask sometimes in short notes. So it's needed for them to know about what is its slightly. I have given only a little differences to make it revise what we have discussed, so that we can see in the next class of the lecture number 3 regarding various drugs according to the question paper point of view and also the syllabus. Thank you.